Hello everybody and welcome to this session on calculating Excel formulas faster using short-circuiting and progressive filtering. Wow! So what is this Excel formula short-circuiting stuff? It's part of Excel's clever calculation engine that enables it to only execute part of the formula rather than all of it. If is the best example. So in this little formula here, if 1 is greater than 2, we execute the part of the formula in red, sum A1 to 1000. If it's false, we execute the part of the green part, C1 to 1000. We don't execute both parts of the formula. So why do we want to do this? Well, it enables us to handle and bypass errors. It makes your formulas more efficient because you're only executing part of them rather than the whole thing. Problem is, not all the functions that you'd expect to short circuit actually do. So we need to have a way of testing which functions actually do short circuit and which ones don't. And we'll look at that. And then we'll look at array formula short circuiting to see how that works. To test functions to find out whether they short circuit or not, I'm going to use this Visual Basic VBA pass value function. It's a very simple little function in VBA. You can see it over here on the right. This is the text for it. And we can use it as any other function in Excel. What happens is we give it a parameter, 99 in this case, and all it does is it prints that out to the Visual Basic immediate window so we can see what's happening, and it returns the value to the worksheet. So if we actually execute this and click the enter, we can see we get a 99 in the immediate window. Get rid of that. This one's a little bit more complicated. I've got a pass value function that's being multiplied by 2, and then it's returning its result to the pass value. So we've got 2 calls to pass value. So if we see what happens when we do that, we return 88 to the worksheet because that's the final value. But the first thing it does is it executes the first instance of pass value, which is got the 44 parameter, and executes that. So we get 44 in the immediate window. That gets multiplied by 2 to give us 88. That's passed to pass value. Let's use the pass value function to see what happens with the if function. So we've got an if, got this formula, if 1 is greater than 2, execute pass value 1, otherwise execute pass value 2. So with any luck in the immediate window, we'll only see one of these values popping up. You can see the final value it returns is 2. Let's execute it and see. Okay, we get 2 in the immediate window, but we don't get 1. So that pass value 1 part of the formula never got executed. This is short-circuiting in action. Well, we know that if short circuits, we've just tested that, these are the other candidates of Excel functions that might or might not short circuit. They've mostly got conditional stuff in them, obviously, because, you may need to make things choose, but I've added let in there because, that usefully could short circuit, although I'll show you, in fact, it doesn't. Now let's test some more functions to see which ones short circuit and which ones don't. If we look at ifs next, well, if short circuit, surely ifs short circuit as well. It's a convenient way of packaging together multiple nested ifs. So we'll execute it and see what happens. We get 6, 8, and 9 in the immediate window. So no, it doesn't short circuit at all. Look, it's executed that part of the ifs function, that part, and that part, and that part, even though it only actually needed to execute the second part. So sadly, ifs does not short circuit. So of course you can do the same thing with if, but it's sort of, it looks a lot clumsier to when you've got all these nested ifs, which is why the team introduced ifs instead. So we'll get rid of those in the immediate window. And then let's see what happens when I execute this one. I only get one value in the window. Let's trace this through. So if false, do pass value 11. Well, it's false, so it won't. So then it passes on to the second if, which says if false, do pass value 20. But it doesn't do that. So it only executes the final one. So you can nest short-circuited ifs and they work wonderfully. What about choose? That's another sort of way of doing things. I like choose as a function to use. I think it's great. Now, let's get rid of it and let's execute the choose function. We get 13 and we only get one value in the immediate window. So yeah, it has short-circuited. So the way choose works, of course, is you give it a number as the first parameter, and the number is what decides which of the following arguments are going to get executed. So we gave it a 2, so it skipped over the pass value 12, did the pass value 13, and ignored the pass value 14. Okay, so choose is a good function, not like that wretched ifs. Finally, we got switch, which is kind of similar to choose, but works slightly differently. So we give switch a number, and in this case, you can also use text. And it looks for a match. So does the 2 match the 1, in which case it'll execute pass value 21. 2, it'll give you pass value 22. 3, it'll give you pass value 23. Well, we can see the results 22. Question is, does it short circuit or doesn't it? It doesn't. All 3 of those pass values get executed, even though the only one it actually needs to execute is the pass value 22. Shame. And what about error handling with if error and if NA? Do these short circuit or don't they? Let's check it out. So here's the if error. So it's seeing if pass value 1 returns an error. If it does, then it'll move on to pass value 2. Otherwise, it'll just return whatever's in the first value. So we execute it, and we only get the 1. So if error is a short-circuiting function, jolly good. Very good for error handling. We don't get to execute both the potentially error part of the function and the what to do if there is an error part of the function. What about if nah? It's a sort of weaker brother of if error. So if pass value 1 returns NA, then do pass value 4. Otherwise, don't. So we execute it, and we get 3. Okay, if nah short circuits as well as if error. Good news, useful functions should be used all the time. And what about let? So here we've got a very simple let function. We let variable 1 be pass value 1, variable 2 be pass value 2, and then we actually return the value of variable 1. So variable 2, pass value 2, is never used in this function. So it would be good if it managed to short circuit that. Sadly, it doesn't, as we'll see here if we execute it. It executes both the 1 variable and the 2 variable function, and then finally returns the value that's been stored in the 1. It's a great pity about that because let is really neat way of making your functions more usable, more readable, and in a lot of ways more efficient because you can eliminate duplicate calculations within one formula. But sadly, it doesn't short circuit. There we go. But what about dynamic arrays? How does short circuiting work with dynamic arrays? Well, suppose we've got this little formula here. So we've got beta, and we're passing the if function for trues and false values. And so it's going to return 4 values as a dynamic array. So how many calls to pass value is it going to make? If it was split up individually into individual statements, we know that we'd only call pass value 4 times. But maybe if dynamic arrays don't actually short circuit, maybe we'd have to do both of them in the dynamic array version. So it could be 8. I don't know. I kind of thought, when I started thinking about this, I kind of thought the answer was going to be 4 somehow or other. I thought it was going to do something clever. Let's actually see what it does. It'll clear out that immediate window first. Now let's execute the function. Wow, we've only got 2 values. We've got one value of 80 and one value of 90. So what it's done is it's only executed past the pass values once. So it executed each of them once. Somehow or other it's stored the values somewhere, and then it's cycled through the if, trues and falses, and returned the appropriate values from the pass values. Actually, what it's really doing under the cover is it knows it's got to return 4 values, so it scales up the single value it gets from pass value into an array. So we get an array containing 4 80s, we get an array containing 4 90s, and then it looks at the trues and falses and decides which value it's going to return from the arrays. Wow, pretty clever. So that's really efficient, despite the fact that dynamic arrays don't actually short circuit. Great. Now in this case we've we've only given pass value a single parameter, so it's only returned 1 value. So we've got 2 scalars to choose from. What happens if instead we pass an array or a range or something? Well, pass value is not going to like that, so I've got a slightly different version of pass value called pass value A that stringifies the output. Okay, so here we go. So we're passing it either the first time 1, 2, 3, 4, and the second time 5, 6, 7, 8. So we can see here that it's returned an array. I've stringified it into a string, and those are the results we get. Let's just execute it to see what happens. Yeah, we can see that again, the pass values only get called once. They return an array, and the if statement decides which of the arrays it's going to return. Now, of course, Excel doesn't know what to do with arrays of arrays, which is what it's trying to return, which is why I had to use a stringify function to turn the array into a string so that my pass value would still work. The VBA version of pass value A is pretty simple. I've just added a text join function in the middle there to stringify the array into a string. We've seen that in the case of if and dynamic arrays, we don't get short circuiting. So we probably won't with ifs, choose and switch, but I guess we ought to check just in case. So let's look at the ifs case. We'll execute that function, and we get 1, 3, and 5. Okay, 1, 3, 5. No short circuiting taking place. Get rid of those. Try choose. Choose did short circuit on its own. So what's it going to do with dynamic arrays? No, doesn't short circuit. But it's still doing this efficient trick with dynamic arrays anyway. So we don't really care. In fact, the dynamic array behavior is better than short circuiting anyway. Switch, yeah, 1, 2, 3. Okay. So let's summarize what we found out about short circuiting within a formula. There are 4 good short circuiting functions: if, choose, if error, and if nar. There are 3 bad short circuiting functions: ifs, switch, and let. With dynamic arrays, well, they don't short circuit, but they've got a very special trick that works extremely well. Now let's look at another kind of short circuiting. I call it progressive filtering. This is where we're doing something like a sum ifs, and each condition only looks at the rows that pass the previous condition. So in this sum if formula, we're summing A1 to A10,000, and the conditions are that B1 to B10,000 equals ABC67. And then only the rows that pass that test will get passed to the next criteria, which is column whether column C is greater than 500. So that's quite efficient, or can be. The trick is, of course, to rearrange the sequence in which you put the conditions. So what about filter function? How does that work? Well, we're going to compare a few filter funcs. Let's look at sum ifs versus filter and versus sum product. Sum product basically works the same way as filter, although it's commonly used to do this kind of sum filter kind of calculations. Here's the data that we're going to use for the tests. We've got a table of shipments over here. There are 10,300 rows in it. We've got these columns. It's shipments from country to country, within the from country, from city to city, and then the date that the shipment was made and the value of the shipment. And we've got set up a set of criteria here, 21 rows of 4 criteria. So we want to find all the shipments that are from this country to this city on this date, between this date and this date. So quite a lot of criteria conditions. If we look at the total number of filter comparisons we want to do, we've got 21 rows of criteria, so there's 21 of those. There are 1, 2, 3, 4 filter conditions that we want to do, and there are 10,300 rows. So we're going to do a total of 21 by 4 by 10,300 comparisons. Now, if we can do this as a progressive filter, this is what happens. This is the count of the number of occurrences of that from country within the 10,300 rows. So AT, Austria, occurs 404 times in the 10,400 rows. So if we do the first filter just on from country, that's going to do 10,000. For each of these conditions, we're going to do 10,000 comparisons, because we're going to go through all the rows looking for from country is AT. And then for those rows that pass that condition, we're going to look at the other 3 criteria. So I'm going to do 3 comparisons for each of the from country counts. So for the first criteria, we're going to do a total of 10,300 plus 3 times 404 is 11,512. So if we add all that up, in the pure filter case, where we're doing all the comparisons, we're going to do 865,000 of them. In the progressive filter case, we're only going to do 247,000 of them. That's a significant gain and should result in much faster calculation. So let's run the comparison. First case is SUMIFS. So that's this formula here. And if we time the calculation, we will see how long it takes. And it takes 14 milliseconds. Okay, which is quite fast. There's not really a lot of data here. Okay, so we can see that the first criteria we're running on is the two country. So in this, the first one is going to be the number of values in for country AT. If we do this with filter, then it's this formula here. So we do a sum of the filter of the filter data values, which is in column F, and then for each of the conditions we run, that's the date count condition, start date times end date times the from country and the to city. So this is we can see that's we're going to do an awful lot of comparisons with this calculation, and we'll time it and see, and it takes about 50 milliseconds. 43 milliseconds on a good day, 50 milliseconds on a slow day. So yeah, it's a lot slower than SUMIFS. So is there a way we can make filter itself do a progressive filtering calculation? Well, yes, there is. This is let coming to our rescue. So here's how we do a progressive filter. We start by doing a let that sets up a value called pre-filter. So that's doing a filter of the total shipments of all the country data that equals, so it's column A is the two from country, looking at the filter condition. And then we pass that to the other conditions. So we've got a value of pre-filter that's storing only the rows that pass that first criteria. So we're only doing the other criteria calculations against the subset of rows that we've calculated in pre-filter. So that's very similar to the way SUMIFS works. And we time that. We can see it's only taking 15 or 16 milliseconds. So it's very, very similar to SUMIFS. So we've managed to do, using let, we can build progressive filters into the filter function. Now the advantage of the filter function, of course, is it works with arrays, and which SUMIFS does not. So it's a rather more flexible kind of calculation to use when we're using dynamic arrays. It's a great pity that there isn't a filterIfs function which works with dynamic arrays and automatically does all this progressive filtering. But there you go, we don't have that at the moment. Conditional filtering is often the slowest thing in your workbook, but you can use progressive filtering to speed this up. SUMIFS and all the other similar if style functions automatically do progressive filtering. Trick is to put your most restrictive condition first. But of course they only work with ranges, great shame. Filter, on the other hand, doesn't automatically do progressive filtering. It does work with ranges and dynamic arrays, and you can use let to create a subset within the filter formula and pass that to subsequent criteria. That's just as fast as using SUMIFS. We've seen how to speed up filtering using progressive filtering. But if your data can be sorted, there's an even faster way of doing things, using what I call the slicing sorted data trick. The idea is that you find the first and last rows in your sorted data. That'll delineate a contiguous block of data, and then you can extract that slice as a range. We're going to test it on 500,000 rows to see how fast we can make it go. Let's look at the data. So we've got 500,000 rows of transaction data. It's sorted by period within GL. We've got a concatenated column, which is concatenating the GL and the period to make life simpler for us. Now we could do all this in, when we're landing the data using Power Query, or however the data is going to arrive within the workbook. So let's see what happens if we use our progressive filter technique we learnt about in the last period. Now, first of all, we'll do so we've got a GL that we want to extract. We've got a start period and an end period, and we're going to use a filter, standard filter, based on the transactions table, with the GL number being equal to B4 and the transaction period between start period and end period inclusive. So that formula retrieves a few thousand rows and takes, I think, about 70 odd milliseconds. Oh, it's going slow at the moment. That's 135 milliseconds. Let's try it again. You never know. 84 milliseconds. Well, he was running at 73 earlier on. Anyway, quite, not too bad, but could be faster. So if we run it with progressive filtering, which is we define the pre-filter as being the filter to get out a subset of data, which is just the GL code data, and then we filter that subset of data on the start period and end period. So if we time that, let's see what we get. 27 milliseconds. Okay, it's faster than the 30. So we can see it's quite a lot faster than the standard one. That's what we found earlier on, so we're not too surprised. Now, let's see what happens when we use our slice technique. We need to start by finding the first row and the last row for this GL number, and between the start period and end period inclusive. So finding the first row is easy enough. We can use Xmatch. We can tell it option 1 to find the exact match or the next largest, because maybe the start period, maybe there are no transactions for that start period. So in that case, we want to find the next largest transaction. And we're going to use, as a search method, we're going to use binary search ascending. Now, binary search is a search method which is lightning fast compared to linear search. Linear search starts at the beginning and looks at each row in turn until it finds what it wants. Binary search, on the other hand, operates on a divide and rule principle. So it looks in the middle, finds out whether the value it's found is above or below the value we're looking for, and then looks in the remaining, discards one half, looks in the other half, and repeats the process until it finds what it wants. This means that it's using a very, very small number of comparisons, which is what takes the time, of course. So it's very, very fast. If we look at how long it takes to actually do this, we can see that it takes less than 1 millisecond. That's fast on our 500,000 row transaction table. Finding the last transaction, the last row, is not so easy. We've got to jump through a few hoops. First problem is that binary search always finds, when there are multiple entries, binary search, which there are in this case, binary search always finds the first instance. So that's no good. So we need to look for a value that's one more than the end value, and then subtract 1. Now, there are a few other little gotchas in there. Binary search, if you try and find a value which is beyond the end of the transaction table, you get an error. So when we look for the last period for the last GL, we're going to have an error because we're looking for end period plus 1, and that's not going to work. So first thing we've got to do is to, by the way, we've got to calculate end period plus 1. So we do that by extracting the last digit of the period, adding 1, and reassembling it. Now, okay, it's going to find, it's looking for 202313, which doesn't exist, of course. But that's not a problem because we're always looking for the next largest if it doesn't exist, and then we subtract 1 to get us back to the value we really want to look for. Now, if we're looking for the very last record in the whole transaction table, we're going to get an error because we're looking for a value that's beyond the last value because we've added 1 to the end period. So we've got to do a quick correction fix for that, which is we find what the row is for the last transaction. So we do this with this formula. So we take we get the row of the very last transaction, which is by using take minus 1. We subtract from that the row of the transaction table, which is take transaction period 1, and then we add 1. So that gives us the total number of transactions in the table. Now then, so if we get an error when we're looking for the last row, we will use the last transaction instead. Okay, so is that all we need to do? No. Then we've got to assemble we've got to extract the actual range of rows that we're looking for. So we do that with a double index statement. So we look at index of all the transactions using C7, which is the first row within the transaction table, and the first column. So that's the top left-hand corner of the block of rows that we want to extract. And then this second index gives us the last row of the transactions and column 4. So this construction generates a range that goes from the top left-hand corner of the block we want to the bottom right-hand corner of the row we want. And it's using the range operator colon in between the two index statements because index returns a range. So that gives us a range that spans the block of rows that we want. Now we've got to do a little error checking here, error handling. So we say if the first row is greater than the last row, we've got an error. Otherwise, we're going to use the first row and the last row we found. Okay, so it's a little bit more complicated than you like, but it's fairly straightforward, really. We've added in a lot of error handling to cover all the corner cases of like what happens if you're looking for something that doesn't exist, what happens if you're looking for something that's before the first row in the transaction table or after the last row in the transaction table, or there aren't any transactions in the range of periods that we're looking for. So all those error conditions will be handled. Okay, but how fast is it? That's what we want to know. So let's time it. Profiler, calc range, and it's taken 0.73 milliseconds. It's 0.7 milliseconds. I mean, that is lightning fast. The progressive filter took 30 milliseconds. So, I don't know, at least 30 times faster. And at 0.7 milliseconds, I mean, you're never going to notice this. Even if you've got hundreds of these formulas within your workbook, you're never even going to get up to a second. So that's fantastic, and a really good, nice trick for doing very fast sorted slices. Summary. Okay. We find the first row, we find the last row, we do index to extract the slice out, and then it's fantastically fast. We can only do this if the data is sorted, but that's fine. Usually we're extracting the data out of a database or data warehouse or something or other, and so we're probably using something like Power Query to extract it and land it. So we can do the sorting and concatenation of general ledger and the time period to produce that extra column in Power Query as we land it in the data, in the workbook. And once we've landed it, of course, we can play with it dynamically at incredible speed using this kind of technique. What do you think? So let's summarize what we've covered in this session. We started by looking at in-formula short-circuiting. And we found that if, choose, if not, and if error were good functions, they did short-circuiting. But ifs and switch were bad guys. They didn't do short-circuiting. Dynamic arrays, on the other hand, don't do short-circuiting, but they've got their own magic trick, which is really fast. Then we moved on to filtering. So we started by looking at the way SUMIFS works and how it's worthwhile putting your most restrictive criteria as the first one, because it progressively passes only the rows that pass the test to the next criteria. Then we looked at how filter works. It doesn't do progressive filtering, but we can make it do it by using let, and that can speed up filtering quite a lot. Then finally we looked at slicing sorted data. What a trick. This is using binary search, which is a lightning fast searching technique compared to linear search. It only looks at a very small numbers of the rows in what you're searching compared to linear search that looks at all of them. We use that in combination with the index to index range formula to extract a slice of data using binary search to find the first and last row, and then the index to extract it. And that was the lightning fast. So that's a good, neat summary of what we've covered in this session. Thanks for listening to this session on 3 ways to short-circuit Excel formulas. I hope you enjoyed it, and I hope you're still here. If you want any more information, then you can look at my website on decisionmodels.com. That's got a lot of information about Excel, how to make Excel formula, about the Excel calculation engine. And my blog, Fast Excel blog, has got a whole pile of information on how to make Excel go and VBA and other stuff go faster. Anyway, I'll be around hopefully after this session ends to answer any questions you may have. Look forward to that. Bye.